Hello. Good evening, everyone. Hey. It's science night. This is great. Thank you for joining us. My name is Kim Ryder. I'm the Director of Operations here at the Wayne Theater. And on behalf of our staff and our ambassadors, our amazing volunteers, and our board of directors, we welcome you. We welcome all of you here. So it's great to have you. Before we get started, I just want to tell you a few things that are happening here at the Wayne. Let's see. This weekend, you are admiring right now the set of Romeo and Juliet. Yes, we had our opening weekend last weekend, and this weekend we are going to be closing the show, so Friday night, Saturday night, and Sunday afternoon. And tickets are still available. We'd love to have you come back and join us. Let's see, later on in March 4th.
Possible to offer programs like the one you're going to see this evening. Last year I had the opportunity to attend the Our Karst Landscape and Water Quality Symposium that was coordinated by the Shenandoah Valley Soil and Water Conservation District. Despite having dedicated my career to understanding and addressing the various impacts to the water quality in the rivers and streams of the Shenandoah River watershed, the presentations at the symposium expanded my understanding of how the Shenandoah Valley's topology and geology influence the movement, quantity, and quality of both the surface and groundwater in our region. Understanding this interaction between these water systems is essential for everyone living in the Shenandoah River watershed. Our actions, whether it's farming, development, or everyday life, has a direct impact on both the surface and groundwater. By recognizing the interconnectedness of these water systems, we can work together to ensure the health and sustainability of the Shenandoah River and its surroundings ecosystems for generations to come. It is my pleasure to introduce our guest speaker this evening, Wil Orndorff. Wil is a native of the Shenandoah Valley of Virginia. He grew up looking for caves on the family farm and adjacent abandoned quarry. Introduced to formal caving work at the age of 18, his interest in caves, karst waters, and geology grew into both a career and a lifelong passion. With a bachelor's degree from Johns Hopkins and a master's in geology from Virginia Tech, focusing on Appalachian tectonics in hand, Wil entered the professional karst world as a self-employed consultant performing karst analysis of the potential impacts of a proposed high-voltage power line corridor on karst springs and bat habitat along its path. Becoming Virginia's karst protection coordinator became Wil's career and afforded him the opportunity to do the work he loved, protecting the resources he cared about. The nature of the job turned Wil into a jack-of-all-trades karst who wears many hats: geologist, hydrologist, conservationist, educator, explorer, and increasingly a biologist. That's quite a list. His work has resulted in the establishment of 2 natural area preserves protecting significant caves and additions of several tracts containing significant caves to extending preserves. Through the Virginia Department of Conservation and Recreation's Environmental Project Review, Wil has helped to avoid and mitigate impact to hundreds of caves with the help of the Virginia, you're going to have to help me with this one, Speleological Survey. All right, with whom he is a director at large in his spare time. Wil is the 2019 recipient of the Karst Award from Karst Waters Institute. He lives in Blacksburg, Virginia with his wife, Zena, who has some tales of her own that I heard during dinner. Thank you very much, Wil, and welcome.
Hello. It's really great to see so many people here tonight, a lot of familiar faces. And I'm going to be able to free range tonight because I have this lapel microphone, so it's a little bit dangerous. One thing I would like to, I'll just kind of start over here, but one thing I would like to say is all this, stuff that, quote, I have done is all built on the shoulders of giants. A lot of people in cave and karst stuff are folks who do this without, we do a lot of stuff without getting paid, but they get paid to do this for work as well. Vast majority of the knowledge on caves and karst that we have in the U.S. and probably around the world comes from people who are just plain interested in it and collect that information and do some of the best exploration and science work that goes. And I'm really honored that some of those folks came out here tonight to listen to what I have to say. I was asked to talk about surface and groundwater interactions in Shenandoah Valley, and when you're a karst person, or surface and groundwater, they don't really mean that much. It's just water. It goes under the ground. It comes back out. It may stay under the ground for a little while. It may stay under the ground for a long time. But water is water. And those distinctions that people like to put in a regulatory manner and things like that really aren't terribly valuable, particularly in karst landscapes. The slide here, and it's a little bit bright in the room, but I'll try to tell you, if this were a little darker, you'd see this is a pretty intense turquoise blue. And this is the brown. Now, this is actually not the Shenandoah River. It could be. This is the Powell River down in Lee County. But to me, this really kind of caught sort of what people conceive of groundwater versus surface water. Surface water, muddy, turbid. Groundwater, blue, clean, beautiful. And this is sort of the idealized world we'd like to see, where water flows out of a spring that makes our surface waters cleaner and it improves them. What you're going to see tonight is that this simple little picture, which is really cool, is not really how these things work. Okay, is this going to work? Try again. Okay, we have a clicker failure, unless I'm using it wrong. Let's see. Can you advance to the next slide there? That's not me. This is the largest karst spring in Europe. All right. Ah, there we go. Okay, so there's lots of definitions for karst, and I apologize for our artistic shadowing of the screen here. But to me, the definition I've kind of settled on for karst is that it's a landscape that's been significantly influenced by the dissolution of the bedrock. In karst landscapes, you tend to find water draining underground. That's one of the most common things in a karst landscape. The water's going underground, and you have relatively dry surface environments. You see things on the landform that are kind of unusual. You see streams that disappear. You see places, big springs, where streams reappear. You see places where the earth has collapsed in on sinkholes. And some places you see openings in the ground, and you go in those openings and you find hundreds of feet to miles of passages that extend underneath the ground. We call these things caves. Karst is most commonly developed where you have soluble bedrock, where the most common soluble bedrock is. And globally, that's limestone and dolomite. Those are carbonate rocks. That's because they're combined with a cation, calcium or magnesium, plus carbonate, CO3. This stuff is produced geologically in shallow seas where you have a lot of red algae fixing these minerals from the seawater. And then somehow they end up in the Shenandoah Valley, on the top of Mount Everest, and all these other places. But carbonate bedrock is what most karst is developed on. This is a map of carbonate bedrock in Virginia. And you can see we're sitting, right here is Waynesboro. So we're probably right in that part of Waynesboro right there. Here's 64 coming in from Charlottesville. But you can see we have this karst bedrock pretty much running up and down the I-81 corridor in Virginia. If we go and look at the planet as a whole, we can take a sort of a bigger picture and kind of work our way back down to the Shenandoah Valley. Any place you see this reddish color here, that's where we have carbonate bedrock, and that's where we have karst around the world. Blacksburg's here, where my office is. We're just right next to there in Waynesboro. Slovenia, over here in Europe, is the place where the word karst comes from. It's an area called the Kras. And their terminology that they use to describe these landscapes is a lot of the terms that we use today. If we zoom in just to the U.S., we can see a map that was made by our colleagues at the USGS. And this shows the distribution of karst around the U.S. And you can see carbonate karst, the blue, is by far the most common places. We get some evaporite karst out in New Mexico, where our daughter's running around right now, in Arizona. You get some other karst here and there, carbonate aquifers. You get some basalt, which probably shouldn't have been on this map because it's not karst. It's pseudokarst. But anyway, that's where the karst is. And you can see here in the Appalachian Mountains, we have this belt. And that belt of karst is repeated sort of at all scales. Like as we go from here over to West Virginia, to eastern West Virginia, we cross belts of limestone outcrops. The Shenandoah Valley just happens to be one of the bigger, thicker belts in which these carbonate rocks are exposed. If we can zoom in a little bit more, we can see the karst of the Appalachians. This is sort of an arbitrary definition. It has the Appalachian Mountains and the interior lowland plateau. This was a thing called a landscape conservation cooperative unit the Fish and Wildlife Service had. And we talked them into including karst as part of their studies. So Dave Culver, who's a Virginian, also did a bunch of work in here. What percentage of these little squares in here are karst? And you can see a lot of the areas in the Shenandoah Valley are anywhere from 40 to 100% karst, depending on where you are. I mean, we're sitting right here in Waynesboro, so we're in one of those blocks that's like 40 to 60%, about half karst bedrock, being half underlain by carbonate rock. If you go here, this shows Virginia and West Virginia. I'm not used to such a big screen, so my resolution's not quite adequate, and I apologize for that. But you can see here, this is the West Virginia line. We're sitting over here in Waynesboro. Here's where I grew up in Strasburg, near Ogden's Cave and some other small caves up in that area. Skyline Caverns is over here. And this map shows the distribution of karst bedrock. It also has little dots that are indicating the caves. It's hard to see that on this particular scale. I was lucky enough to see both of my co-authors of this poster. Bill Balfour, I saw him today out in Giles County. And Phil Lucas happens to be here tonight. So I got to see everybody on this map here today. But this just gives you an idea of how this belts of carbonate bedrock characterize the Appalachians. And again, one of these thicker belts constitutes what we call the Great Valley karst. And at DCR, we have actually, for purposes of workflow and also for purposes of kind of the characteristics, we've kind of divided Virginia's karst into the Great Valley region, the Highland region, where several of the guys here tonight have done a whole lot of work exploring and mapping caves, the New River Valley region where I live, and then the Mountain Empire region down here in extreme southwest Virginia. And each of these areas sort of has its own characteristic styles of caves. The cavers always say Great Valley, where we are now, has lots and lots of show caves and not so many big caves. Highland region, lots of big caves, especially in a couple areas. New River Valley region, some pretty big caves out in here. And then in the Mountain Empire region, has caves of all sizes and stripes and ages, and is a real spectacular area. So karst is more than just caves. Caves are one of the outcomes of karst processes of dissolution. I'm going to talk more about the process because that probably has more to do with the water than just the cave component itself. This is the classic karst dissolution chemistry. I will try to get through it quickly. But basically what goes on in karst is you have water. We'll just model water for now as H2O. And water dissolves carbon dioxide. That carbon dioxide is being produced in the soil by soil respiration. When the water comes down to the soil and dissolves CO2, it makes a weak acid called carbonic acid. The carbonic acid, just like any other weak acid, dissociates into a hydrogen and some bicarbonate. That hydrogen reacts with calcium carbonate to produce calcium ions and more bicarbonate. Waters with a lot of bicarbonate are called alkaline waters. And if any of you guys have well water or good local spring water you're drinking and you go to the store and spend money on alkaline water, you're being a fool. because you're already getting alkaline water around here. Okay? We got lots of bicarbonate in these karst waters. Let's see here. So bicarbonate waters are the characteristic thing of karst. And that means their pH tends to be between 7 and 8, and they tend to be able to hold a lot of dissolved ions. All right. So, of course, karst and surface waters also contain some other things, not just these chemicals that we talked about. They contain sodium, can come from natural sources, can come from road salts. They contain nitrate, which can come from fertilizer applications to fields and from septic systems. Chlorides from road salts. They contain sulfates that have both natural sources and anthropogenic sources. It's hard to see it because of the light, but over here they also have these chemicals that are hard to detect, so maybe that's appropriate. This actually represents atrazine. Anybody know what atrazine is? Yeah, it's pre-emergent herbicide to keep things other than corn from growing in your field. Okay? So you get these different things that we put on the land that end up in our water. We also, believe it or not, if you analyze water from around here, you're going to find caffeine in it. Those are supposed to be coffee beans. Okay? So because we drink coffee and then we use the bathroom, it goes down through our septic systems, we find caffeine in the groundwater. We also find pieces of remnants from our shampoos and other personal care products that we use. In addition, we find some of these represent mud, some of these represent the other things coming through your septic system. But you find sediment, and you find waste from animals, humans, etc., things that have come from that. One of the things that comes from that are these pathogens. So the water that you see in the surface stream or coming out of a spring or coming out of a well is not just H2O. H2O is a chemical. Water is a mixture. One of the cool things we see in these caves around here, in these karst systems, are animals. This is one of about 200 cave-limited animals we know from Virginia. That particular one's kind of the mascot of the karst of the Shenandoah Valley. It's called the Madison Cave Isopod, and its home's right here in Augusta County, a few miles up the road in Grottoes. It's where it was first discovered. So I encourage people to think of water like this. Okay? It's not simply a solution, again, or not simply a chemical. It's a solution, and it's a suspension, and it's also a habitat. It's got things living in it. It's got things that's carrying along in suspension, and it's got all the things that are dissolved in it. So water is a soup, really. It's very hard to find water that's not got a lot of stuff in it. It's a universal solvent, and it's fairly viscous. So again, that gives it these properties. Now, when we collect water for use at a municipal water supply, whether it comes from a spring or a well or from one of the surface streams around here, we treat it. And at these treatment plants, we find what we don't like, we get rid of it, and we adjust the chemistry. Those are the two things, really, that they do at a wastewater treatment plant. The problem is, nobody tests for everything. And there's always new things coming out that get in the water. So water treatment and the water that we use for human consumption or for industrial processes, etc., it's always you're playing a little bit of roulette with water. And that's why watershed protection is so important, because everything you do in the watershed gets into the water. It may not be in high concentrations, but some of the stuff, like these contaminants of emerging concern, BPAs, for instance, other things, these come out and they can cause lots of health problems we don't even know about. So it's good to be water aware and good to know where your water comes from. Let's see. So especially, like I say, in karst, whatever's applied to land surface is going to end up in wells, springs, and your surface waters. All right, that's my depressing PSA for the evening. So here's sort of an idealized view of a karst landscape. That's what geologists would call a block diagram. It's if you were in an airplane, you had a giant bulldozer and cut out one side and then the other side, and you could see what was there. These represent trees, give you an idea of scale. But this is a diagram from, there's dozens of these you can find on the internet. I like this one because it shows a lot of features at a nice angle and a lot of things that we have around here. What you see here is a landscape surface where you've got limestone bedrock, and underneath of it, you've got a non-limestone or non-carbonate bedrock, in this case, a shale. Over here, we've got areas where you have some other cap rock, maybe a sandstone that's dwelling. And we see this situation in Virginia a lot, where we've got water that's flowing off of a mountainous region like the Massanutten Mountain or North Mountain, and it flows downhill, or Jack Mountain out in Highland County, and it flows down until it hits the limestone. And what do you think happens with that water when it hits the limestone? It finds its way underground. It finds its way into these solution cavities, and then it continues to make these caves and these conduits larger as it works its way through these systems. And over time, you develop this natural system, which is where you've got the upland, it's shedding the water. We call that the allogenic zone, okay? Meaning coming from off of it, goes into the karst, flows under. When it flows under the karst, sometimes it takes surface material and removes it through the subsurface. When that happens, we get sinkholes. Okay? And you'll see sinkholes all over the place. Our friend Dave Hubbard, who's another one of the people with this Virginia Speleological Survey that was mentioned earlier, he mapped over 55,000 sinkholes in Virginia. And he estimates that's probably only about 10% of the number of sinkholes. So these are real common features. The water that goes underground eventually coalesces into underground streams, and it comes out as springs. And these springs typically form where surface streams have cut down through the carbonate bedrock and have intersected the water table, intersected one of these conduits. So when the land surface intersects a conduit above the water table, you get a spring, okay? A groundwater spring. So that just gives you an idea. And here, of course, that wasn't me. All right, so here are, did I do that somehow? There we go. Okay, it's great. Okay. So anyway, here we go. And you can see caves, which we'll talk a little bit more about later. Like I said, talk isn't just about caves, but caves feature in. But that gives you a good idea what the landscape looks like. Water goes in from here, concentrated, comes in here more diffuse. It all collects underground, and it flows out of springs and gets pumped up through wells. So that's your basic karst hydrology. How does this look like for real? Well, this is a picture of actually over in West Virginia. Could have been taken in parts of the Shenandoah Valley. But this shows a sinkhole plain. Whoops, go back there. In each of these features, you can see a house here for scale. They're pretty big. And these are individual sinkholes. I ask school groups, what are these? They're like, it's craters. It's like the surface of the moon. These are where meteors have hit. Like, nope, these are places where the surface has fallen in and produced sinkholes. So you'll notice there's no real discrete surface streams visible in this image as well. And all the flow of water is where? It's underground, through underground streams. And can you see where they are? I can't. And that's why if cavers don't explore them, we have to resort to other ways to find out where these underground streams are. We know where the water goes in. We know where it comes out. So here's some of the more, zooming in a little closer, some more of the landscape features. Here's an example of a sinking stream. This is near I-81, and this whole stream comes off virtually upstream of I-81 and sinks in here, goes through a mile-long cave, and comes out at a spring. You also get streams that are a little more subtle. This is actually just over here in Rockingham County near the Augusta County border in Dry River. And this is a place where during the summer you walk downstream and the stream just disappears and all you have are stream cobbles left. And that's because these cobbles, we'll talk more about this place in detail later, but those cobbles all cover up a buried sinkhole complex, a buried bunch of carbonate rock. But you wouldn't know that was there because you can't see it. It's buried underneath of those cobbles. You also get in some of the areas where you have really pure limestones, you have these, what we call karin. It's where there's very thin soils because there's very few impurities to leave behind when the rock dissolves away. And in these areas, are really sensitive to contamination because you don't have any soil to attenuate anything. So if you do like an agricultural landscape use, for example, most of what ends up on that land goes pretty quickly down into the underlying karst hydrological system and doesn't have like soil processes to help remediate those or remove those nutrients. Some of these land use practices are a little bit more blatant. This is actually a picture, I think, from out in Bath County of a farm where we've got the outhouse sitting here. And I've been in outhouses similar to this one where you open the door and you go in and you realize it's not just sitting on the edge of a sinkhole. They actually found a hole to put the outhouse over. So one of the traditional land use practices was to use sinkholes for waste disposal, even for human waste disposal. In Bowling Green, Kentucky, historically, they would have people sort of witch for fissures, and that was how they dealt with Bowling Green's waste from houses. They simply pumped it into caves. Okay? That's since been cleaned up, for the most part. Let's see. All right. Here's another picture of a feature. This is not a natural feature, but this is another way we interact unfavorably with karst. This is a stormwater basin, and this is down in Wytheville, Virginia, right on the I-81 corridor. And here, they had at one point 9 different sinkholes within this single stormwater basin. And that's because they dug the basin up. They didn't worry about the fact they were on karst. And when the basin started filling with water, the water found its way down into the underlying caves and conduits in the karst aquifer. Eventually, this was repaired after we showed it at a meeting where the people who owned the basin, or the engineers for them, were at the meeting, and they decided they didn't like the press. So they did fix it. But there's ways to prevent this. But if you're not aware of karst, this is what you're going to get: is all this soil and all this stuff from these basins going down into the water, plus everything else that ends up in there. This particular basin had water runoff from a Walmart and Lowe's parking lot, and a whole bunch of places where tractor trailers were parked right by there. So anything that was shed into that parking lot went right into the groundwater at this location. And this is not uncommon. Some even more egregious examples is people like to dump things in holes in the ground. It's like, I have trash, I need a place to put it, there's a hole. Brilliant idea. Okay, so this was a very common traditional land use practice, was for people to have a sinkhole and use it as a way to dispose of things. This particular one has affectionately been named the Sinkhole from Hell. It's in Rockbridge County. And cavers volunteered their time, and with a little help from some of the cave conservancies, to get a track hoe, and they cleaned all these tires and all this trash out of this sinkhole. Again, this is not a one-off. There's hundreds of these such dumps around the state, and people have cleaned up a lot of them, and there's still some that are waiting to be cleaned up. The biggest one I've ever done had 22 tons of tires and 25 tons of municipal solid waste. So let's go underground. Let's do something fun for a change. We've talked about all this, the surface ones. Let's see what the underground part looks like. So if you're going to go underground, some of these caves you have to go down a rope to get into. Not all of them can you just crawl into or walk into. And if you're smart, what you do is you train your offspring to rig the ropes and put them down in caves for you. So this is my daughter Naomi, Zena and I's daughter Naomi, who's rigging the rope for us. The rope, I think, was probably purchased from that guy sitting over there. Anyway, and she learned how to rig, so she rigs, and then we always send Zena down first, and then she goes down. But anyway, this is just a way to go in the cave, and some of them have vertical entrances. When you get down in the cave, you can see all kinds of great things. You can see waterfalls where water's coming in the way you didn't come in. This is a waterfall in New River Cave. You can see, is there any way to get those lights down a little bit? Yeah, somebody can figure that out. There's some really great cave pictures coming up. Much better. Thank you. All right. So you can see here water flowing in. So these waters mix underground. Here you've got water that's coming down a passage on the side where it's really rich in dissolved minerals coming into a stream that isn't as rich with dissolved minerals. And you get these beautiful formations where these waters coalesce. Some of the caves, as you guys know, have been developed so people can go in and members of the general public. This is from Luray Caverns over in Page County, which is, I think, the second most visited commercial cave in the world. Here's a picture from Grand Caverns over in Grottoes, Virginia, right here in Augusta County. And then in Virginia, we're lucky. We have a bunch of show caves. You can see the list of them over here on the left. In Shenandoah Valley, we've got several others. There's Skyline Caverns, has these anthodites. Endless Caverns is over here. Really nice, big, long cave system. This is Melrose Caverns up near Harrisonburg. Has a lot of historical signatures from the Civil War. And then Shenandoah Caverns up in Shenandoah County. The only cave with an elevator in it in Virginia. And it's actually a really nice cave, too. They have that goofy guy there, but it's a really nice cave. You have all these wonderful resources. And I encourage people, if you're not a caver and you want to see caves, these are great places to do it. And every one of Virginia's commercial operations is a little bit different. So it's really worth investing the time and the money to go see these. Again, it gives you a chance to see some of that wonders of the Virginia underground. Here's some pictures from some undeveloped caves. You can see the passages are pretty large and pretty extensive. Okay. And this is a cave down in Lee County, real wide place right along. This is the bedding plains of the rock. Where you can imagine how much water must have moved through there at one point. Okay. Another cave. This one you can see some of the human uses. In this particular cave, they dropped a well pipe from a hole in the roof so they could pump water out of the cave to use for human consumption. Not that different than what you're going to do with the groundwater well, except you may not be able to get to the other end of the pipe. This water coalesces and it forms these underground streams. And these streams flow, sometimes miles and miles. In Missouri, tens of miles are documented frequently. And they come out to form springs. But again, what you can see here is these mixing of waters. You've got the water that's flowing in the stream. Some of this, in this particular case, comes from a sinking stream. And you've got water that's pouring in from the top. So it's water from a variety of sources coming together. You can see places, too. In the Appalachians, the mountains are uplifting and the rivers are cutting down. So you see places and marks indicating where water used to be. This is a cave down in Giles County with a watermark in it. You can see similar watermarks over in Fountain Cave or in Grand Caverns, where the water table used to be higher. And as the rivers cut down and the mountains rise, you see the caves get exposed. Again, eventually this water comes out at the surface. This particular spring is down in Wise County. Here's one from Frederick County. This is a place called Fay Spring. Fay Spring used to be one of the major public water supplies for the city of Winchester until the proximity of I-81 and its industrial operations made it unsuitable for continued use. But all the infrastructure is still there, and it's quite beautiful. Unfortunately, springs are susceptible to what goes on the surface. This little spring is down in Montgomery County, Virginia, and if you were to look in the distance and could see maybe through this tree, you might see some bulldozers this day, because that's where the Mountain Valley Pipeline was built. And during the construction of the pipeline, some sedimentation appeared at the spring. And we had connected the spring to the pipeline corridor via some dye tracing, which I'll talk just a little bit about later. But again, springs are susceptible to what we do on the surface. And this is just one example I had to show that. So what I want to do now is talk to you guys about some case studies. It's pretty easy to speak in generalities and say, oh yeah, the water picks up chemicals and sediment and diseases, and it goes underground, it comes back up. But that's all generalities. Why don't we look at some specifics from the Shenandoah Valley of how we know these things and some of the more kind of interesting things we've learned over the years about how these systems work. So I want to talk about three things. One is North River, which is the North River is part of the North, Middle, and South River, which come together to make the South Fork of the Shenandoah River. And this we're going to be talking about over in the Mount Solon area of Rockingham County and Augusta County. Then we'll talk a little bit about the Madison Cave isopod and what we can learn from where it lives about surface and groundwater interactions. And then finally, I'd like to talk about the epikarst, which is that area between the land surface and the caves, and how that may function in terms of connecting surface and groundwater. All right. An apology for the resolution here, but you can see here, I hope, this is a mountain ridge. And then here we have these structures. This is the Shenandoah Valley here. So this would be North Mountain right here. And North Mountain has these gaps that cut through North Mountain in this area. And at each side of these gaps, this is Dry River. This is a river called Briery Branch. And this is one called North River. And where they come through the mountain, they spew out these huge trains of cobbles. And one of the neat things about these cobbles in this area, and you can see here just the labels, there's some geological faults and things showed here. Each of these blue represents a surface stream. Okay? And each of these dots represents a spring. But these cobbles, a lot of times of year, these stream beds, you walk down, they're completely dry. Now, if I followed this thing upstream to the right, and I walked about a mile, I'd have several cubic feet per second of water flowing the same time of year. But that water, when it comes onto the carbonate where these cobbles flow into the valley, the water disappears beneath these cobbles. And so one of our big questions is, there's another example, Briery Branch. Okay? Again, dry in the summer, even though there's water flowing through that gap. Nearby, there are a lot of big springs. This is the spring at Mount Solon, which is at the head of Mossy Creek, which is a really famous trout stream that's received a lot of attention recently in stream restoration. This is also in Mount Solon. This is something called the Sapphire Blue Hole. One of our good friends who's no longer with us, back I think 2006 or 2007, he dove this area. He's a cave diver, a guy named Ron Simmons. And what was really funny about this was we went out and we talked to the guy. He's like, I raise trout in here. It's going to be okay. He's like, oh, yeah, I won't mess with the trout. Well, Ron got his cave diving stuff on, and Ron dove in there, and he went down into this spring head, exploring it. Well, all the trout saw Ron's light going down into the dark, and the trout all followed Ron down into the bottom of the spring. And as it coalesced, the passage got tighter and tighter, and the trout were more around, and finally Ron's like, he got to where he couldn't really go on comfortably anymore, plus there were all these fish. So he turned around, came back up to the surface. Well, the trout didn't follow him back. So he had a situation where, it was kind of like the Pied Piper. He led all these trouts down into the aquifer, and they didn't come back. So needless to say, the owner at the spring was not very happy with Ron at this time. Fortunately, about a day later, all the fish showed back up at the surface. But anyway, that's kind of a fun story of kind of the shenanigans you can get into with this kind of exploration. This is a Silver Lake Spring, and this is actually the dam at the bottom of the pond. I'm sure a lot of you guys have been to Silver Lake up in Dayton. And this deposit here over the dam is all natural mineral deposits that are deposit where the water flows over the dam. Kind of indicates how rich that water is in dissolved minerals. This is one more spring. This is called the Crest Spring. And this particular day, we were out there with the USGS collecting some samples to work some magic I'm going to talk about later. Because one of the things you can do with water, believe it or not, is you can run some analyses on the chemicals in the water and tell how long ago it was when that water fell from the sky as precipitation. And so we can get an idea from looking at the stuff that only the USGS could afford to do, and get an idea how old the water was coming out of the spring. Another thing we did, this man's in the audience tonight. This is Waynesboro's own Josh Rubenstein, who's over here. And he's here dumping some dye in the creek or in the river to see before where it sinks, to see where it shows up. So we traced the water to the springs by using dye, and then we analyzed the water to find out some more of its secrets using these techniques that the USGS had. So we found out some really, really neat things. First of all, we found out, and we was talking about this with some people at dinner, you don't always find the dye. We had a hard time with a couple of these traces. The dye went in and never came out. However, we had some good traces. This was the one where we determined that North River sinks, comes underneath Natural Chimneys area there, and pops out at that spring at Mount Solon we were. Up here where Dry River sinks, it comes out and becomes Beaver Creek. So those were the dye traces we got. The ones we lost, we'd like to redo someday because it is a little confusing when you lose dye. You always wonder, where did it go? But some of it might have gone deep, and it may still show up. Because when we looked at the USGS stuff and in the springs in light of the dye traces, we got dye traces came to this spring. Dye traces came to this spring. They didn't come to any of these springs. And when we look at the age of the water that the USGS determined, these springs were anywhere from 25 to 45 years old in terms of the average age of the water. So here you have this little paradox, right? We've got these springs that superficially look the same, and in some places the water was underground for an instant, a week, a month, maybe a year. Other places, the water's been underground for a long, long, long time. And these springs are all in close proximity to one another. It's a very complex system. We did notice some other things about the springs. We noticed that these springs that were younger tended to have softer water, tended not to be as alkaline. The pH tended to be a little lower. The ones that were older tended to have more dissolved minerals, as you might think. And that's probably because they were circulating deeper within the aquifer and had a longer residence time, but probably more the depth than the residence time. So we determined that there was two types of springs like we just showed there. The autogenic, deep-seated, old springs, and then the allogenic, dominant, which means water flowing in from off-karst, quick-flow springs. Yeah, that's pretty neat, from a nerd perspective, right? That's really interesting for a geology perspective. But when the rubber hits the road in terms of water quality, is you have to think about how these springs are going to behave in terms of susceptibility to contamination. A spring that gets water that sank yesterday, if you dump some contaminant in that sinking stream, it's going to show up very quickly, right? That stinks. But you know what's nice about it? It's also going to clear out pretty quickly because it's a quick flow system. So I like to think of these springs as sort of acute in the sense of they are subject to acute impacts. You get a spill, the spill comes in, hopefully the spill flushes out. These, which at face value we would think are a lot safer springs, are maybe a little more dangerous in some ways because that's got 40, 50 years worth of human activity integrated into the water that's coming out of that spring. There's a spring up here, Lacey Spring near Harrisonburg, where they've done a bunch of best management practices nearby to try to improve the groundwater quality. And my understanding is to date, there's been no changes. And we don't have any data on that, but I would bet you that that water has a good a large old water component, and that we're not going to see the results of these best management practices for years to decades, because the water has a long time to move through those systems. So I kind of think of these systems as chronically impacted. They may not show, a real big response to an individual spill, but over time, they're going to integrate that history of what goes on in the watershed. All right, so I want to talk a little bit about the springs of Virginia. So Joel Maynard, who's a once-in-a-while caver and a boater and all kinds of things, but he works for DEQ, and he's their groundwater specialist in the western part of the state. So therefore, he works in karst a lot. And Joel became very interested in springs, and he's put the Springs of Virginia database together. One of the things he will acknowledge right off about it is it's mostly not his work. He's integrated from other people. And I think the third most cited source in there is actually the Virginia Speleological Survey. And that was data that was accumulated over the years by Phil and Charlotte Lucas. Phil's here tonight. And it was a huge database that, again, was gathered by people, by individuals who were just interested in it. It wasn't like a systematic government or agency initiative. The one thing you'll see, though, from this database is it makes you think that all the springs are in the Shenandoah Valley. And that's because Joel's office is here. Right? And Joel will acknowledge that this database is incomplete. And it's always a big concern when you publish something like this. People will say, oh, it is written. This is where Virginia Springs are. Forsooth, we have the publication. And that's just not true. So when you read in here, it's like, this is a start. This is an open file report. This is the beginning of an attempt to understand the springs. And when you go down here, guess what sits right there where all the springs are? Yeah, exactly, Virginia Tech. There's a lot of springs there. Down here in Southwest Virginia, we have places where DCR has worked because of biological significance. And there's a lot of springs identified. So this is definitely a very biased database, but what Joel has created is a framework which we can now populate and have a better idea of the distribution of springs throughout Virginia. Because remember, springs are where that groundwater returns to the surface. So the takeaways from the North River study is that the nature of springs can vary over really short distances. There are springs are where groundwater becomes surface water. Again, some of these springs are acutely impacted very quick. Others take long times, decades underground, for the water to circulate through the system. So again, the young springs are easily contaminated, relatively easy to clean up. The old springs, not so much. Case study 2, the Madison Cave isopod. So this guy has long been a fascinating creature to cave biologists. Back in 1958, a famous cave biologist from Kentucky named Tom Barr was with a guy from Stanton named John Holsinger, and they were over in Madison Saltpeter Cave and crawling around, and they saw these things swimming in the lake, and eyebrows were raised because this is what's called a cirrholandid isopod. Cirrholandid isopods are a marine group. Now, there's some places in the world where you find these kinds of isopods in caves and in groundwater, but it's almost always close to the ocean. So what was this guy doing in the Shenandoah Valley? And I still don't know exactly how it got here. That's a discussion for another time. But what we do know is it's an unusual thing. It's the only marine lineage cave animal we have in the Shenandoah Valley and in the Appalachians, for that matter. In addition, we know that it has a few different populations that are genetically different. So it's been isolated over time into separate areas. We also know it's been isolated a long time based on these mutation rates, millions of years, and that its ancestor left the sea between 20 and 74 million years ago. So it's an old lineage here. It's restricted to the water table and below in the Shenandoah Valley, and it's protected under the Endangered Species Act. Actually, it's funny, what led to its protection also had to do with water. The one cave where it was known at the time it was listed, down next to Grand Caverns and Grottos, the town was putting a water tank on top of the hill. And they was concerned about the cleaning and maintenance of the water tank, flushing chlorinated water and stuff off into the sinkholes in a nearby area. So the listing was partially in response to that proposed water tank. Since then, we've discovered maybe another 14 or 15 locations for this guy up and down the Shenandoah Valley. But it's a pretty special creature nonetheless. Fish and Wildlife Service, a few years ago, they were always concerned with these species. You're always trying to figure out what can we do to protect it and should it still be listed. And very little was known about the habitat. So my crew at DCR, we wrote a grant proposal with Fish and Wildlife, and we got the money to do some habitat monitoring. So these sites you can see up and down here are the places where we decided we would monitor where the Madison Cave isopod lived. And of course, being naive, what we thought is we'd go in and we'd find out, well, it likes this particular water, this particular temperature, this particular clarity, this particular hydrology. And what we found out is, of course, that we were wrong. This was our setup. We had tubes that had conductivity temperature loggers in them. We had other tubes that had pressure transducers to measure the water level. We also had turbidity sensors, which turbidity is how the water transmits light. So the clearer it is, the lower the turbidity. Okay? So we wanted to see how these systems were in terms of these very fundamental properties. We also collected some water chemistry samples that I'll mention about here in a little bit. But what we saw was this. These are our sites. The wells are over here. The caves are over here. What we saw is the sites varied crazily. Some sites, the water level hardly ever varied. Other places, the water level varied insanely. Look at this, 10-meter water level variation at that site. Okay, 4 meters here at 3D Maze Cave in Rockingham County. Madison Saltpeter Cave, about 1 meter over here at the type locality. So we said, well, that's crazy. Lots of variation, more than we expected. Then we looked at the temperature. So everybody always tells you that, well, cave temperatures are 11.8 degrees C in the Shenandoah Valley. Well, some were, some weren't. We've got this cave called Power Plant Pit, which is up around 13. We had some that were colder. And we had lots of variation in temperature at some sites over the course of the year. This one place would go as low as 6 degrees C, and all the way up to 22 degrees C, okay, in response to precipitation events. Other ones, like Madison Saltpeter Cave, which is where the thing was first found, you could calibrate your thermometer. The temperature did not change over 8 years. Okay? So, go down here to specific conductance. Again, Madison Saltpeter Cave, almost no change. Some of these other places, fairly variable. Front Rural Caverns down off Route 340 near Skyline Drive had quite a bit of variation. And the conductivity values varied from 800 down to 400, depending on where you were in the system. Some showed more variation than others. Again, if we're trying to characterize a habitat, we kind of expected to find some more uniformity across these different sites. And we just didn't see that at all. Some of the really interesting things, for instance, this power plant pit cave here in Brother Dave's Cave, this cave and this cave sit right beside each other. They're literally 100 meters apart, and the water is a 1 degree C difference in temperature, always. Obviously not connected most of the time. So we were getting a lot of complexity that we did not expect in the system. And that's just looking at your averages. If you look at how the systems respond, things get crazy. Now, this is like an EKG for the groundwater here, okay? But what you can see is here we have the water level at this particular place, the temperature, and the specific conductivity. You'll see the patterns are different from site to site. And you don't need to look at this in detail. I'll show you sort of a simpler example here where we can see it a little bit more clearly. But what I wanted to show you this is that things are variable. Things are reactive. Things are responding to precipitation. You can see here, this is one I'm going to zoom in on here in a minute. But this is those two caves that were right close to each other, Brother Dave's Cave and Power Plant Pit. Same time scale, right next to each other. Look how different this graph is from this graph. Very, very different behavior, even though they're right next to each other. So when we go out, right now the Department of Environmental Quality is working on having groundwater monitoring wells across the state of Virginia. Their goal is to have 1 well per county. This is literally within an area smaller than the residential lot I live on. And there's that much variation. So how do you get representative data? 1 well is not enough, for sure. So we look at Power Plant Pit and Brother Dave's Cave, we get to see some really interesting things here. We see that when we have a rainfall event at Brother Dave's Cave, we get, this is the specific conductivity, yeah. This is how hard the water is, how many minerals you have in it. When it rains, Power Plant Pit becomes less conductive. Rainwater comes in, it gets softer. At the same time, Brother Dave's Cave right next to it does exactly the opposite thing. It gets more conductive water into it. And so we were really puzzled by this. And I'll tell you what we think is going on here in a minute. If we looked at the temperature, we would get Power Plant Pit would always show these big spikes. In the summer, it would get warm. In the winter, it would get cold. Again, the rainwater washes in. Brother Dave's Cave, whenever we had rain, it would, what did I do there? Okay, there we go. Whenever I had rain, the temperature would go up. Every significant rainfall event, temperature goes up in Brother Dave's Cave, then comes down. Okay? What is going on here? And then if we look at the water levels, the relative levels, we would see Power Plant Pit have these huge levels that slowly decay. Same event at Brother Dave's Cave, these tiny little increases. Never much, never much. I think the biggest increase we ever had was about 1 meter during a huge storm, okay, where we had about 6 meters here. So it was a lot of difference in terms of the behavior of these two systems. So what we finally figured out was happening is that Brother Dave's and Power Plant Pit had different elevations. And then when you dumped enough water into Power Plant Pit, it would force the water from Power Plant Pit to backflood up into Brother Dave's Cave. And so that more conductive water from Power Plant Pit was getting shoved over into this other adjacent cave. And then it would settle back down over time. Now, why is this interesting from a layperson's point of view? Well, suppose you had contaminants in one of those systems. And then you had a big storm come in. you could get water backflushed into a system that's adjacent that all your monitoring wells and everything would tell you would never be susceptible to what was going on over here. And this was a real kind of eureka moment for me as to understanding that these tales that I'd heard about things doing this weren't just people making things up. You get these weird hydrological phenomenon, and the only way to understand how these things work is to monitor them and do it with like a lot of data, okay? And do it carefully. All right, so we looked at all these sites, and I'm not going to go through the details on this. What we found was a whole bunch of different behaviors at different sites. The ones that had the strongest surface water connections showed these big changes in response to precipitation events. The ones that had less surface water influence didn't show as much change. The place for the species that we were studying, the type locality, was the most anomalous of it all, because at Madison Saltpeter Cave, nothing ever changed. The water would go up a little bit and down a little bit. That's it. Conductivity didn't change. Temperature didn't change. A little bit more about this. We talk about what happens on the surface getting into the water. And groundwater is surface water is groundwater. If we go to Front Royal Caverns, which is in Warren County, and which lies under Route 340, guess what we find overrepresented? Chloride. Road salts. Okay? Salination. So over time, you get this higher level of road salts in the waters of Front Royal Caverns. What you can't see quite as clearly here because of the shadow is over here at Urban King Well and also something called the Howard Tabb Well. Those are in heavy agriculture areas. One's in a barnyard, others next to a cornfield. This is nitrate here. So where we've got heavy agricultural land use, we get higher nitrate in the groundwaters. EPA drinking water standards here. 3 of our wells were in excess of the EPA drinking water standards, and they were all in heavy ag land use areas. Power Plant Pit also had high chloride, and that's adjacent to some large industrial facilities and warehouses up there in Warren County. And then Madison Saltpeter Cave, the type locality, again, plots down here. A little bit of nitrate, almost nothing as far as chloride goes. It really, like, this is your really good water down here, at least to a first approximation. But you can see how much variance we had across the species range at these different sites. What was also really cool, not to go too deep into it, is that between events, the more stable sites never changed. Like, that's actually 6 points right there. It's always the same. Okay? These other places that were more proximal to developed land, they showed a lot more variability in terms of the measurements that we took. Okay, and for the turbidity, we saw the same thing. Here's Power Plant Pit and Brother Dave's Cave again. We would see, only in really big events would we see any turbid water in Brother Dave's Cave. Most of the time, we didn't see any turbidity response at all. But every time it rained, Power Plant Pit would get muddy. And only when it backflooded into Brother Dave's would we see that turbidity affect that other cave, right next to each other, right next to each other. Final thing I think I'm going to say about this one is one of the other things we did was we analyzed the isotopic composition of the water. Our friend Dan Doctor at the USGS did that. He looked at the oxygen and hydrogen isotopes. And what he found out by comparing these, if you plot these, you have a characteristic plot for annual rainfall, which is here. You have where precipitation samples over the course of the year fall along this line. And then you have the mean groundwater winter precipitation, which is that circle. Okay? The groundwater all clustered where the circle is for winter precipitation. The way this is interpreted, and we'll see some more things I think that will support this view, is that the groundwater is mostly precipitation that fell during the winter, like any farmer will tell you, right? If you want your wells and springs to be good, you need some big snows in the winter, right? Because that's when our aquifer is going to get recharged. And we were surprised it was this clean of data. And we'll talk a little bit more about this in a minute. So the study takeaways from the second case study is the system response varies over short distances. And you can see these consistent differences at different sites across the study area. There's ample evidence in that data set for negative impacts from surface land use. Okay? As you could see, for the ones that were close to roads, close to ag fields, they had chemical signatures that were very characteristic with the overlying land use. Case study 3, the James Cave Epikarst Observatory. It's a fancy name for means we hung some tarps underneath stalactites and we collected the drips. But we use the term the Epikarst Observatory because it sounds sophisticated and gets grant money. Didn't really get that much grant money. But anyway, you can see the setup here. PVC, tarp from Lowe's, duct tape, all the things scientists use a lot of. Lots of zip ties. Anyway, this is underneath some stalactites, collects water, and goes down to a reservoir. And what we did there was we collected the water, we measured the drip rates, measured the electrical conductivity, did some wet chemistry, and basically just kind of got the pulse of what was dripping into the cave. You can see over here this sort of experimental setup with the drip collector, reservoir, a rain gauge for rate, and then a sample bottle. And this is what it actually looks like in the field. This is that same tarp looking from below. You can see it comes down through the funnel, down to our little reservoir, and then down through our rain gauge and into our sample bottle. So that's what we were doing, collecting this data over about 7 years. And here's, I guess, a little 4-year, 5-year snapshot. And this blew our minds because, again, whenever we try to study something, we realize our models are very simplistic. And what happens here is we noticed, oh, it only drips during part of the year. And even when we have a big hurricane come through in the fall, right after the growing season ends, the cave drips don't notice. They don't do a thing. So how do you interpret this? Well, this is just looking at drip rate. Well, does the same pattern show up elsewhere? Oh, I'm sorry, this shows what we call the recharge season, okay, being highlighted here. So that's the area, time of year when water is actually making it through and being pushed into the aquifer. We also looked at specific conductance. Again, how hard the water was. And we saw some crazy patterns here. During that recharge season, the conductance was responding like crazy all over the place. Once the recharge season ended, then the conductivity slowly goes up and then it slowly goes down. Each of these represents a different site in the same cave. Same thing in the next year in 2013. The drips stop, conductivity slowly goes up, then it slowly goes down until the next season kicks in. So what we determined from this, or thought about this, is that what happens is there's this reservoir, leaky reservoir between the surface and the cave. And this thing fills up slowly, and then once it's all filled up, then a drop in the top means a drop out the bottom. But until that cascade is full, you guys, I'm sure, have all seen people have those cascading fountains where you have one reservoir emptying into another, That's what we think is happening. But they're leaky. So when those reservoirs leak out, until they're primed, until that pump is primed, you're not going to get any water through the system. So in the summer, when it's warm, all this is overlain by soil. And during the summer precip events, the plants eat up all that water. They take up all the water, and very little makes it through. So the leaking is taking place faster than the refilling of the epikarst during that time of year. So we don't have any connectivity to the system. You can see the same thing in the cave stream flow. This is a young caver from Blacksburg, Megan Junod, who worked on this. You can see during the winter, the stream really responds to precip events. Look at these big precipitation events in the summer. Stream doesn't respond. Did this one. But they don't really respond much. In the dormant, off the growing season, any little rainstorm will increase drip rates and increase the stream flow. Okay? Again, showing that intermittent connectivity to the surface. So what are our takeaways on this? Well, water only makes it past the plants when they're dormant. Okay, that seems to be pretty evident. As the growing season lengthens and temperatures rise, okay, if that happens, we get longer growing seasons and temperatures rise, as appears to be the case, there's going to be less aquifer recharge unless precipitation patterns change accordingly. Because simply more of that's going to go up into the atmosphere and up through plants, and less time of the year for water to make it into the aquifer. Another thing that's, I think, important about this is it shows us the importance of the epikarst in stormwater management. One common thing that people like to do in karst around the country is, I'm going to take my stormwater, I'm going to send it right into the aquifer. And they think the aquifer is down there below. It's the phreatic zone. It's below the water table. Well, what we found out from this project is that a lot of water gets stored between the water table and the surface. And that water isn't susceptible to forcing water out of a spring as fast as the water at the water table is. Okay? It doesn't contribute to the hydrologic head on the aquifer. So when your stormwater management implication for this is that you need to have the water stored discreetly high on the landscape so it can work its way slowly down through that system and not just injected down into the aquifer below the water table. All right, so all this stuff that we've talked about technically here, I felt obligated to give you guys at least one quick slide about, well, how do we address this stuff from a regulatory perspective in Virginia? And Virginia does okay. We have a Cave Protection Act, which some people in this room are actually involved in getting passed. The Cave Protection Act designates some caves as significant. It has a cave board that provides counsel to interested agencies. Does a lot of good things. We have Department of Environmental Quality and the State Water Control Board. And they have some things that address karst. The stormwater management regulations are an ongoing battle to get them to address karst, but they do, and they're increasingly doing so. Solid waste regulations, can't put your landfill on a sinkhole, that kind of thing. The 401 certification, project-specific certifications, like for pipelines and all. When the controversial pipelines came through a few years ago, they were karst provisions that were required in those certifications that turned out to be somewhat effective in reducing the impacts. In addition, land application of biosolids, sewage sludge, and also animal biosolids, poultry waste. All that stuff has some limitations where you can apply it if sinkholes are present, for example. Department of Health addresses septic system siting and addresses waterworks regulations, some minimum criteria that the water has to meet. Other laws that come into play to protect karst indirectly are the Endangered Species Act, like we saw with the Madison Cave isopod. The State Endangered Species Act as well. There's a few more species that only have state status. And then at the EPA level, they do some more stormwater control about how you can inject fluids into the subsurface. And there's special provisions for karst. And then there's local ordinances that are present throughout the state. And there's some question as to, how constitutional those are in Virginia because of something called the Dillon Rule, which means that unless otherwise specified, state law has precedence. So that's kind of the set of regulations that we have in the state and tools that people use to try to check water quality, protect the karst as best we can. So what does this all mean? Get over here so I can actually see my list. This picture, by the way, is a great picture. Zena took this in the summer of 23. This is a photo of a guy who came up from Texas to learn all about our cave bugs in Virginia, a guy named Ethan Perrin. And Ethan's sitting down there looking at the Westlake and Madison Saltpeter Cave. Anybody know what the stuff on the surface there is? Calcite. Yeah, calcite rafts. This water is so rich in dissolved minerals that when it gets exposed in the cave, it precipitates minerals on the surface, like a layer of ice. And if you go there and you disturb it, which I'm allowed to do because I'm looking for bugs, that will sink. And the water is the bluest, most beautiful water you've ever seen. In the entire study we did there, we never found a measurable turbidity value. In other words, the light always transmits through there perfectly underneath that, what looks like broken glass on the surface. So anyway, great picture. And we always thought this is the place we go to ponder these issues. But what does this all mean? I would say that in the Shenandoah Valley, most groundwater was recently surface water. And much of the surface water that you see in streams came out of a spring. So it's also groundwater, or was discharged in the bed of the stream. Especially in karst, what happens on the surface is going to impact the groundwater, and that in turn becomes surface water. So there's a connection. This water is water. It's going in and out of the ground, in and out of the system. The other thing is, that sounded really simplistic, and it is, because, it's a very general statement. The details that I hope you saw from what these three studies is that they're very complicated. The more I learn about this, I like this axiom, the more I learn, the less I know. Sure, I've got much more facts and observations, but I am much less certain about how this stuff works than I've ever been in my life because I know too much about it. And in the deeper a dive you make in this kind of thing, the more you realize how beautiful and complex, fascinating, and frustrating the world really is. What it tells me is if we're going to understand and live in a compatible manner with these systems, we need to understand them better. Like you can't protect a cave unless you know where that cave lies. You can't protect the water unless you know where that water comes from. And that requires monitoring and science. Like I said, in Virginia, we've been really fortunate on the cave side because we have so many people in the cave exploration community who've mapped out so many of these caves. And if one thing I will tell you about the cave part of it is that every couple of years, we have the new biggest cave or the new deepest cave. Okay? So it's kind of neat. Like you can be a deep sea diver, you can be an astronaut, or you can be a caver. Those are the three ways you can boldly go where no man has gone before. The final thing I'd like to say is that the population growth, land use changes, and climate changes are stressing the water supply systems. And I don't just mean like what we drink or use for industry, but also what supplies our rivers and surface flows. This is being stressed in karst areas and beyond. And if we're going to keep putting more people out here and developing more industry, we better have a better idea of what's going on and do some planning to sort of avert disasters. So anyway, that's what I have to say. I'd like to take any questions. Yes.
Thank you so much. This was so informative and taught me a lot that I didn't know. A question I have is, well, first off, you talked a lot about contaminants and how they move through and show up in karst formations. But what lasting impacts do anthropogenic influences have on karst formations over geological time? Is that well understood at this point? And how can you situate that within the context of climate change?
Okay. So the question was how contaminants over time can have an impact with karst formations. By that I think you mean like karst aquifers and karst hydrological systems. And how that can happen over time and how could that be associated with climate change. Okay, it's a big question. I would say that contaminants over time, that legacy contamination is most evident in these older karst systems where the water has long residence. You can take a quick flow system, it can be cleaned up. We have a cave down in Lee County where the cave had no life in it. And then we cleaned up the contaminant source. And within 10 years, Thompson Cedar Cave, everything's back, everything's hunky-dory. But you take one of these springs that's 30, 40, 50 year old water, and that water is showing this trend of increasing nitrate or increasing atrazine or other chemicals. Even if we stop what we're doing today, that trend may not reverse for a while. It's hard to turn an iceberg around. And so I think from over, it's not quite geologic time, but over human time, you see this happen. Over geologic time, the asteroid's going to come eventually. So, over geologic time, there'll be a reset. But over human time, we can see these things, and over historical time, we can see these impacts. For climate change, I alluded to that earlier pretty directly, and I think the problem we have with climate change is every karst system, kind of as we discovered, wherever people settle an area first, okay, or whenever a particular group of people came into an area and settled it, they based what they were doing on a certain hydrological regime. And you sort of got used to that, right? What we're seeing now is if we have lower recharge, if we have longer growing seasons, we have changes in precipitation patterns, these systems are fundamentally going to change in terms of, and we don't know how they're going to change. Yeah, I can sit up here and I can tell you, well, longer growing season, less recharge, we're going to see decreased spring flows, decreased groundwater levels. But that could be totally overwhelmed by increased precipitation. So there's, again, I think a lot of monitoring that needs to be done and a lot of preparedness for multiple potential outcomes. And I think when people plan to use, we should have 2 million gallons of water a day we can take from this spring. I think and that's based on their peak amount they think they can have. They need to cut that in half because we need to be more conservative in estimating how much of the stuff we can use. The last big drought we had in 2002, 2003 in the northern Shenandoah Valley, it was starting to look a lot like Las Vegas up there. And, and not by shiny lights and stuff, but, it was looking a lot like water restrictions are coming into use. We can't get water anymore. When it rains a lot and recharge is going through, people forget about it. But when we have droughts, people remember. And I think that we're going to see more of that in the future. Yep.
Our local economy here in Waynesboro has always been kind of water related, from DuPont coming here to our future's probably going to be water related also. We have two major springs, Squinter and Jefferson, that feed our public water system. Any comments directly on that particular, the springs right here in the Waynesboro area? Are they old springs, or are they long-term or shorter term?
Okay, I will first caveat it that I don't have any USGS data from Coiner or Jefferson Spring, because I don't think they were included. What I can tell you, though, geologically about where they're situated, I think they're more likely to be better off than springs in a lot of other places in the valley. And the reason I say that is you're here on the west toe of the Blue Ridge, and so you've got a lot of vegetated area, forested area in the watershed that probably feeds these springs. In addition to that, you got a lot of precipitation because you're right here with that orographic precipitation where the weather systems move up over the Blue Ridge. If you contrast that to like the area in the North Fork Shenandoah River around Harrisonburg, for example, where you get only 30 couple inches of rain a year in the watersheds where those springs are, and the land use is a lot different in those areas, I think those springs are a lot more susceptible. That said, any of these springs that are used for public water supplies need to be monitored, and I think most of the public service authorities that operate these, most of the utilities, do a pretty good job of monitoring for what they know to monitor about. But in terms of stuff like having good age dating information and things on all these springs, that's very expensive work, and even though it's very valuable, it's stuff that people are unlikely to want to expend resources to determine. So you got to get lucky enough to get the USGS to show up and do it. So, that answer your question? Yep. Yep.
I noticed where I used to live that if there was an incredible amount of rain, then these springs would start popping up out of the ground, and it would just be pumping out of the ground, and we called them wet springs. What's the mechanism for that?
Okay. So the question was, after big precipitation events during wet times, we have these springs that just appear out of nowhere. What's the mechanism there? Well, springs, again, are places where the water table intersects the land surface. And it's not just the water table or the potentiometric surface, but it's a place where a conduit, a pathway, intersects the surface, and the water can rise to the level within that pathway. We had a really great example of this in 2018, which was the wettest year on record. We're up in a place called the Arabian Plain in Clark County, which was just a big dry section in Clark County, kind of northwestern Clark County. All of a sudden, it became this area that was just full of springs. And it was like that for 9 months. And it was because the water table had reached up and those conduits were intersecting the surface below the elevation of the new water table. And as long as that excess precip was coming into the system, which it did in 2018 for a long time, these ephemeral springs kept running. In most cases, these little springs like you're talking about might last a few days or a week. So, yes? This is a great question. So the question is, did we find out anything about the preferences of Madison Cave isopod? Yeah, well, a couple things. It likes to be in water. Okay? I'm being smart. But it likes to be underground. We did find out that it has a tolerance for really hard water. And when we went to these places to do biological sampling, and when there had been a recent precip event, a lot of times the animals wouldn't be around. But you have to remember that these places where we find the Madison Cave isopod are just little windows where these animals can come up from the aquifer. Like there's places where we've dropped baited traps down wells. We've picked this thing up from 30, 40 meters beneath the Earth's surface. These animals are incredibly robust, and they can go deep. And so if the turbidity comes in, the water gets too soft, they just swim away, and then they come back. Their tolerance for impaired environments was impressive, though. Like the two places where we had the most continuous site occupancy were the type locality and the most impacted site, power plant pit. Wow. Right? So those were the two places that had the highest occupancy. What does that tell you? You know, they seem to be, people describe them as the, swimming cockroach of the Shenandoah Valley. And they're endangered. In about a second, yes? Well, several of us in here I know have had the experience when we've been in caves and we've heard that horrific sound of water rushing in unexpectedly. I've been in caves when things have been flushed, and I've been in caves where you can see the impact of septic systems coming directly into cave systems. So the question was, sorry, I didn't repeat the question. The question was, wells and septic fields in close proximity, do they talk? And the short answer is, oh yeah, they talk. And there's multiple places around the state where I've flushed dye down toilets and picked it up out of wells or out of springs that people use or seen it in caves. Now, in most of those cases, we're talking about legacy systems. We're talking about things that were put in before the current health department regulations were in place. Now you can't put your drain field in a sinkhole. Now you have to have good testing either by the health department or a certified professional soil scientist. So there's a lot of safeguards in place now. But where I've seen this more regularly is in these older systems, sometimes rural systems that were not really ever approved to begin with. But I think the current system for new construction does a pretty good job. Other questions? Oh, okay, yes, sorry. Is somebody back there? Yes. The greatest discovery I've made? That's a great question. What's the greatest discovery I've made? The funniest discovery I made was recently. I think it's a good story. We were over in a cave called Fountain Cave, which is part of Grand Caverns Park. And a lot of what I do now is I study cave biology. And for years, I've been fascinated by the biology at Cave Hill, which is the area where Grand and Fountain and Madison Saltpeter Cave are. And one thing that always struck me was not just what was there in terms of the cave animals, but what wasn't there. And one thing you don't see there is animals that live in the drip pools. There's no amphipods in the drip pools. There's no isopods, these different crustaceans that are ubiquitous throughout the area, except they're not there. But we've got this really neat fauna in the deep groundwater. So that's puzzling, right? Then I was thinking, well, what else don't we have there? Well, we don't have any of a certain type of millipede there. And we also never seen any cave beetles there. Now, cave beetles are all over the place in caves. There's 50-some different species of cave beetles in Virginia. But never seen one. 50-some years of biology at Cave Hill, nobody ever saw a cave beetle. Pretty impressive, right? So we're in there in November 24, and we're doing a biology trip, and some of the people from Grand Caverns are there with us. And I'm explaining to them about, this interesting biology of Cave Hill. And I said, well, we don't have any amphipods or isopods up in the drip pools. This millipede's not present here. And nobody's ever seen a cave beetle here except for that one running right by down the road. So I think that's my greatest discovery. All right. All right. There's a question over, yeah. Okay, the question was, what kind of bait do we use when we're baiting for stigobites? Stigobite's a term using for any animal that lives, an obligate groundwater animal, a stigobite or a stigobiont. So what do we bait these things for? Well, you do what the master taught you to use. And the master in our world was a guy from Stanton named John Holsinger, who kind of pioneered cave biology in Virginia and the Appalachians. And he said, you know what works best? You take a shrimp, you put it in a stocking so the animals can't access the bait, you tie it off, you put it in a trap. And his trap of preference happened to be an old peanut butter jar. So for years there was the debate over whether it was the shrimp or just the residual peanut butter on the jar that really attracted the animal. But we figured out it's probably the shrimp. But we've used other things too. You know, there's some concern when you're baiting people's wells about shellfish allergies, things like that. So in that time, I might use some salmon roe or something like that I get from the bait store. So, yep.
I noticed we went to Madison Salt River, which is owned by the Cave Conservancy of Virginia. The first cave that they bought is Virginia's longest, deepest cave, Omega, down in Wise County. You done any research on that one yet? It's 29 miles and it is 1,000 feet deep.
Okay, so the question that was asked here is about caves in other parts of the state. There's a cave called Omega Cave System that's owned by the Cave Conservancy of the Virginias, and it's in Wise County, way down in the southwest tip of Virginia. Omega is about 30 miles of passage, deepest cave east of the Mississippi. It's a real impressive cave. You would think, based on the size and scale and everything of this cave, that it would be have some biology that was correspondingly impressive. And the answer is, for cave biology, size really doesn't matter. These animals are tiny. Even a small cave is huge for these guys. Now, that said, it is tier 1 significance, just like a lot of other sites in Virginia are in terms of cave biology. We have 2 different cave beetle species. We have a cave millipede that's known only from the Powell Valley. We have several isopod species that are associated with that cave system. Several springtail species. So there's a lot of diversity associated with it, but it's not more diverse than smaller caves in the same area. It's just when you get in that area with this dissected karst, you really start to see speciation at a very fine scale. Like Burnsville Cove, where a lot of these guys down in this corner have done a lot of work. It has its own characteristic set of fauna. There's animals that are only known from the Burnsville Cove area. You go down to Omega, there's some that are only known from the Powell Mountain karst there, which is Omega and a couple other caves right beside it. And that endemism is what really fascinates me about cave and karst animals, is they really have been isolated. And the theory there about the speciation is that they had a lot of them had this common ancestor that at some time adapted to these different local cave and karst environments. But they're like islands. And this surface ancestor went extinct. But its descendants have made all these separate tribes in all these different isolated cave and karst systems throughout the Appalachians. So that's the general theory for that. It doesn't always hold up. But the funniest one, okay, is with regards to that, there's this guy named Charles Steffen, did his PhD at Auburn. He was looking at pseudoscorpions. Not pseudoscorpions. Yes, pseudoscorpions. Hespercharones was the specific genus he was looking at. And everybody had this one thing called Hespercharones mirabilis. And Hespercharones is a pseudoscorpion, is a ridiculous-looking animal. It's like a scorpion without a tail. And it's got these ridiculously long claws. And it's an ambush predator, just sits around and waits, grabs things, and eats them. But there were Hespercharones all over eastern North America. And what he did for his PhD is, well, I'm going to determine how many species there are. I'm going to do all this genetic analysis. I'm going to show that this is a cryptic species complex with dozens of species. So he collected these animals from all around eastern North America. You know how many species he ended up with? 1. And that became a bigger puzzle than if he'd had 50. And so he's been working on trying to solve that problem. He thinks they must be getting around, maybe on bats. But they move around. Next question. Yep.
Is any monitoring going on in relationship to caves or groundwater
Yeah, so my shop's got yeah, the question is about the Mountain Valley Pipeline and cave and groundwater monitoring. So far, there have been a couple, my agency was involved in that. There's a couple springs that had acute impacts from the pipeline, like the one that I showed there. There's some access issues, so we're not sure about what's going on there right now. As far as the other springs that we are monitoring, some in Giles County, the control and the sample springs are showing pretty much the same response to systems. Early in the construction of the pipeline, there were a lot of sediment releases, and that was one of the things that's easiest to pick up at the springs. It turned out that the erosion and sediment control plans weren't sufficient for the style of project that it was, and after they had some of the earlier issues on the pipeline, the pipeline developers strongly encouraged to reinforce these erosion sediment control measures, which for the most part helped out and worked. There was a karst spring in Newport that was affected when they were trenching under a surface stream there, but once that was done, that spring did clear up. As far as the cave animals go, there is only two caves that really have a direct demonstrable impact from the pipeline corridor. One of them has been known for a long time. We've seen no impacts or changes to anything there, but it's like we're going in every week. The one that had the largest potential for impact was actually a cave discovered during pipeline construction. And at that point, the pipeline corridor was fixed, and they ended up putting the pipe like literally over the cave with a lot of assistance from battlefield medic kind of assistance from people saying, well, if you're going to go over here, you better be really careful, and this is what you got to work with. And they got very lucky and didn't intersect the cave. And there have been multiple trips in there since then, and everything appears to be fine. Now, the thing about the pipelines is, we talk about chronic and acute. You get the acute phase of that pipeline construction is when they're building it. What's going to happen with right-of-way maintenance over time? Time is going to tell. But there's been mostly those acute construction impacts that in places where we have access seem to have mostly remediated. So, okay. Any other questions? Okay. Nope. Oh, yep, one more.
I kind of understand this concept of 40-year-old water in the spring. If there's a flow, there must be a huge inventory, and where is it hang out?
So the question is the concept of this old water at the springs. How do you explain that? Well, if Neil Plummer were here, who's the USGS guy, who's the guru about all this, what he would tell you is that, well, it's not really 40-year-old water. It's water that has an average age of around 40 years. And if you look at different constituents in the water, they'll give you different numbers. And so Neil and his colleagues worked this sort of voodoo looking at the different constituents. One thing they used, for example, was tritium, which was produced during atomic bomb blasts. Another thing that they use is uranium hexafluoride. Not uranium hexafluoride, sorry, wrong. I can't remember what compound it is. I think maybe it's sulfur hexafluoride. But it's a compound that's associated, I think, with the anthropogenic use. They use helium that comes from the mantle. So there's a whole variety of things that they consider chlorofluorocarbons. And by looking at the different amounts and ratios in those carbons, you can assign an age. That Silver Lake spring up here at Dayton, I mentioned that came out to be about 40 years old. However, while that's true, if you go up on Cook's, I think it's Cook's Run, and you dump dye in a field up there, it shows up down at the spring within a few days. So how can that be if the water's 40 years old? Well, it's an average. And so you have all these different flow paths, some that are shallow and fast, some that are deep and long. And of course, I oversimplified it a little bit in the talk here. But again, it's complex, and a spring is an integrator. So all that water that comes out at the spring, what's going on behind that spring head is very difficult to determine. And the chemicals can give us some kind of clue. In some cases, we have friends who can go in there with scuba diving, and the tanks and the skills and the passages are all conducive to actually exploring it. But in most cases, it's only indirect knowledge that we have. But the old springs, Again, it's a whole slew of chemical compounds that are considered. And how much would I hang my hat on that water being exactly 40 years? I wouldn't. It's a spectrum. Okay. Other question? Yes.
What are the implications of potential cuts at the federal level, EPA, research funding, or USGS, which is theoretically could be on the table, and is there contingency planning at the state level to pick up this slack?
Oh, that's a big question for a guy in a state uniform. The question is, what are the impacts going to be from current things going on in the federal government? The first answer is a lot of state programs rely on federal support. So some of what happens at the state's inevitably going to be affected by what happens at the federal level. The specifics are difficult to determine at this time because it's not coming, it's stuff coming down the pipe. One of the things we hear a lot about is, cost share programs and things like that being cut, which are heavily supported from the federal level, which would decrease the likelihood of people wanting to do practices to improve water quality on their farms, et cetera, things like that. The USGS, half of Virginia's, or a big chunk of Virginia's geologic mapping is done in partnership with USGS and with some USGS state funds that come in to help. One of the things they're doing in Cave and Karst, for example, is this state map sinkhole mapping project, which is going up and down the I-81 and other significant transportation corridors, trying to map out in detail karst topography that could be impacted by, say, a spill on the highway, that kind of thing. Really useful for planning, especially if they go to add lanes to I-81 and things like that. So, funding like that by the USGS, if that were withdrawn, it would have a negative impact. We have to find a way to make up that funding at the state level, and it's uncertain whether that would happen. Another thing the USGS does is partner a lot with localities to do water quality monitoring. They did a lot, like Clark County, for example, or Warren County. A lot of USGS resources were put into those counties to help with water supply planning. And that is something that I think a lot of localities rely on, that partnership. So